Okay, so once again, we're on slide 32 now. I want you to use this image to drag the objects, drag the boxes to the correct blue box to finish the statement. Then I want you to fill in the blank, either as increase or decrease. And then finally, I want you to answer the question in the yellow box. Okay, I'm gonna give you guys 5 minutes.
Drag decreases to if distance increases, the force of gravity decreases, and increases to if mass increases, the force of gravity will increase.
Awesome. Thank you so much, Jennifer. I appreciate that. Basically, yeah, that's basically what it is. If mass increases, the force of gravity increases as well. And if distance increases, the force of gravity decreases. You can see the red arrows is basically the force. So as you can see, these ones are a little bit weaker, and these ones right here are a little bit much stronger. Awesome.
I put that it decreases.
Yes. If mass decreases, the force of gravity will decrease. Awesome. Continue. How about for the next one?
It decreases, and then the other one is it increases.
Awesome, indeed. Thank you. Increase. Thank you, Emily. Appreciate that. Indeed.
I said yes, it affects gravity because gravity depends on mass and on distance of two objects.
Okay, because gravity, and I think you said gravity depends on mass and the distance between two objects, I believe. Yes. I'm glad I'm able to hear you again, Jimena. 10 minutes starts now. So about basically we're going to talk about Coulomb's law and the law of gravitation. Basically, we want to know how strong these fields are and these forces. How strong is the magnetic field? How strong is an electric field? How strong is a gravitational field? So in order to know that, we need to apply laws, apply formulas that give us a value that tells us here, this is how strong or how weak this field is. So this is where Coulomb's law and the law of gravitation comes into play. They're both very similar. I will say that they're both very similar. So we're going to see a lot of differences and a lot of similarities as well. So, but the first similarity is that first red circle on the top. It has a definition. It's basically the definition for both of them. They are a formula that determines the strength of an object. Okay, it's a formula that determines the strength of two objects. Sorry, of two objects. So Coulomb's law and the law of gravitation, they're a formula that determines the strength of two objects. Now, what are those two objects? Well, it differentiates between both of them. For Coulomb's law, it's between two charges. So on the left side, on that left white box, you can put two charges. But for the law of gravitation, on the very right side, is between two masses. So they're both formulas that determines the strength of two objects. But for Coulomb's law, it's between two charged objects. And for the law of gravitation, it's between two masses of objects. So think of planets as the sun, stars, all that good stuff. And for two charges, think of protons, electrons, positive, negative, electricity, all that good stuff. Okay. Now, as I move downward, there's a big F in the center. That F just stands for force. Okay, that's force. Now, on either side, you see there is a formula right there. And each of these formulas, they kind of look the same. Don't you think they look kind of the same? On the left side, we have the Coulomb's law formula. We have Q1 and Q2 on the top, which basically just means the charge, like charge 1 of the first object and the charge of the second object. And then on the bottom, we have an R. That R stands for distance. And the K is a constant. It's called the Coulomb constant, which is right here. But we're not going to go too much into detail with the math side of it. Not yet. Okay. So don't worry about the math side yet. On the other side, we have the law of gravitation. And as you can see, the formula is kind of the same. The only difference is instead of Q1, Q2, it's M1 and M2. And that just basically means the mass of the first object and the mass of the second object. And the bottom side, we have the r, so the distance still the same. And then we have a capital G on the side. That's the gravitational constant, and that's the value right there. But like I said, we're not going to go too much into detail with those values yet until next week. What you should know, though, there's a second circle, a second red circle in the bottom. They have the same units. The same units are newtons. That means newtons, we know units, newtons is the unit of measurement for force. And we know Coulomb's law and the law of gravitation determines the strength of those forces. So they have the same units, which is newtons, okay? Now here's a part where they do separate. They do go their own separate ways. On the left side, there is a part that says very blank. I want you to fill that one and put very strong. Very strong. These forces, the Coulomb's law forces, these forces are very strong. Okay, they're very strong. And since they're strong, they can be either attractive or repulsive. So they can either pull you in, attractive, or they can push you away, repulsive. And they're only relevant on small scales, such as states of matter, charges, electricity, atoms, protons, electrons, very, very small stuff. The reason I can touch like the table, the reason I can touch water, the reason I can even touch like the air in the sky is because of Coulomb's law. Their forces are so strong, they basically hold our reality together, which is kind of trippy and crazy. They hold our reality together. So these Coulomb's, these forces have to be very, very strong in order to keep all these states of matter into one place. Okay. And then the next one we have right here on the very far right side, we have the gravitation, the law of gravitation. It's very blank. I want you to put very weak. These are very weak. And since very weak on the bottom, you can put they're only attractive. They're very weak and they're only attractive. That means that they can only pull you in. They're only attractive, which makes sense because it's gravity, right? Gravity only pulls you in. It only attracts. And they're very weak. And they're important on large scales like planets, the universe, black holes, satellites, the moon and the earth, all that good stuff has to do with the law of gravitation, which is crazy because the law of gravitation deals with very big objects, yet they're the weakest of the forces. And Coulomb's law deals with very, very small scales like atoms and particles, yet they're the strongest forces out there. Isn't that correct, Craig? That's not correct. Now I'm going to summarize this real quick as you finish copying it down. There's two main laws, Coulomb's law and the law of gravitation. They're both formulas that determines the strength of two objects. But Coulomb's law is between two charges, and the law of gravitation is between two masses. The formulas are kind of the same. The only differences is the charges and the masses and the constants that they have. And they both have the same units though. They're both newtons. That's how you measure them. And Coulomb's law, they're very strong forces, and they can be either attractive or repulsive when it comes to very small scales, like states of matter, protons, electrons, atoms, all that good stuff. Whereas law of gravitation, they're very weak forces, which means they're only attractive, they only pull you in, and they're important on large scales such as planets, the earth and the moon, black holes, and so on and so forth. That's it. That's pretty much it. So finish copying those notes, please. So as we move to slide 35, okay, slide 35, it has a picture of both formulas. You see, both formulas are right here. And I have a description of these ones for you. So they both look the same, right? They both kind of look the same. The only differences is what object we're focused on and the constant. So for the law of gravitation, m1 is the mass of an object and m2 is the mass of the other object, whereas r is the distance between both of those objects. And then the capital G is a gravitational constant. And if you go to the Coulomb's law, they look the same. The only difference is instead of m1, it's q1, which is a quantity of the first charge, and q2, which is the quantity of the second charge. But the distance is still the same. It's still r. R is the distance between both charges. And then K is the Coulomb constant, which we'll talk more about next week. Okay, so it's a really good visual for you to see that. If you want, if you want a prettier visual, go to slide 36. Okay, so slide 36. I know I'm moving a little bit fast, but that's just to show you. You can always go back and look at your own on your own time. But slide 36 has color coordination, and it basically tells you how they're related to one another, like what's their equivalent for these ones. And it also tells you if it's attractive or repulsive. As you can see, Coulomb's law, it tells you if it's attractive or repulsive. Like opposites are attractive, and the same charges are repulsive. Whereas universal law of gravitation, we know it's gravity, so it's only attractive, so it only pulls towards each other. I think that's a really cool visual to see. So when you get the chance, especially when you do your assignments, look at slide 35 and 36. It'll give you a lot of insight on how to basically complete the assignment. We're gonna go to slide 37. Slide 37 and 38 are basically the same guided practice, except slide 37 is the effect of mass on the force of gravity, and slide 38 is the effect of distance on the force of gravity. Okay? Basically, what I want you to do is I want you to look at these respective figures. And using these figures, I want you to answer these three questions. What happens as mass increases? What happens as mass decreases? As force and mass directly or inversely related? And the same thing for slide 38. And I want you to answer the question by dragging the yellow box to the respective question. As you can see, there's three questions, but there's four boxes for yellow boxes. That means one box will not be used, okay? One yellow box will not be used. So you only have to answer those three questions with using three of the boxes. One of these yellow boxes will not be used, okay? So once again, use a figure to answer the three questions by dragging the yellow box to the correct answer.
Increasing.
Mhm.
And then for the second one, I put force is decreasing.
Indeed. Thank you, Jasmine One. Appreciate that. Thank you. Thank you.
I put that it's a direct relationship.
Mm. Okay. Can you explain, please? How do you know it's a direct relation? How did you get that?
I'm not really sure. I just put that because like since like force is decreasing and mass decreases, like I was like, I don't even know how I got it, but it like makes sense in a way.
Okay. I like that you focus on that. Yes, like you said that when force is decreasing, mass is decreasing. How do you know that's like because they're both the same, right? They're both going down. Or is that what you're trying to get
Yeah.
to? Right. Yes. So that's pretty much that's a great way of seeing it, Sarai. Thank you. It's a direct relationship because when one increases, the other one increases too. And so if mass decreases, force is also going to what? Decrease. So very good job. Thank you so much for that, Sarai. So think of these. If you haven't got a chance, copy these down right now. Think of force and mass as like two BFFs, like best friends for life. Whatever one wears, the other one's gonna wear the exact same thing, right? Because they're like super BFFs. So if mass increases, force will also increase. If mass decreases, force will also decrease. This is known as a direct relationship. They're directly related to one another. So everyone, let's go to slide 38. So this was slide 37. Let's go to slide 38. Now we're focusing on distance. We're not focusing on mass anymore. We're focusing on distance. So let's go to slide 38. So Daniela is putting in a chat box. She said the first one. What happens to force as distance increases? She put force is decreasing. Force is decreasing right there. So what happens to force as distance increases? The force decreases. How about the second one? The second one is force is increasing. So as the distance decreases, the force increases. Thank you, Daniela.
I put that this is a direct relationship because as you can see when it's the distance is 2 in the second example, the force is only 1/4, but when the distance is 1/2, it's 4, like the force is 4. So you can see that there's like a direct correlation to like how much distance and the force of it.
I like that you put the correlation between them. I will say though, it's not a direct relationship. It's actually an inverse relationship. So your nation was actually spot on. You just confused the two wordings because you're using the 1/4 and the 2D, and then you're using the 4F and the 1D. As you can see, they're kind of flipped from each other. You kind of see that 1/4 and 2, and then 4 and 1/2. They're kind of flipped to one another. So this is actually known as an inverse relationship. So think of it as so so you knew how to do it. It was just the wrong wording. So it's actually an inverse. Correct explanation, wrong title. So think of it as an inverse. So just fix that real quick. An inverse relationship because as one increases, the other one decreases. So when distance increases, force will what? Force will decrease. And when distance decreases, force will what? Force will increase. But thank you so much, Alan. Thank you so much for coming off mute. I really appreciate you actually saying that though. So correct explanation, just make sure it's inverse, not direct. This is the main thing. Mass and force are directly related. So if one increases, the other one will increase as well. And if one decreases, the other one will decrease as well. They're best friends. And then distance and force are inversely related. So they're like enemies. If one increases, the other one decreases. And if one decreases, the other one will increase. So they go the opposite direction. So one's really good friends and the other ones are bitter enemies. Okay? And that's pretty much it.